Hi everyone. In this lecture, I'll actually try to cover the question number 2 and 4 in the assignment sheet. Okay, I understand due to COVID, I'm trying to give you hints as to how to solve those two problems. They're pretty simple problems. I'll just take you to the theory of the question number 2 and 4. So the whole intention, as I told you, most of what you have done so far, at least the simulation part and the assignments, a good amount of it, especially in project 1, is something you have already learned in communication systems. So here I'll try to present in a more intuitive way to look at those results, and then we will try to extend those results to the different slightly modified channel models which we have given in assignment number 2. And you will see why did I give those questions. It's pretty logical. Those questions are pretty sensible and pretty logical questions. So we'll discuss that in this lecture. So first I'll start with the standard additive wide Gaussian noise channel for a BPSK signal. Okay. So again, we already discussed, when we show here, I am only showing the baseband channel model. Even a passband channel can be shown as an equivalent baseband channel, right? When you remove the carrier signals, you can show it this way. At the end, you can show your received signal at the end of your sampler, matched filter and all that. The received signal will simply be a sum of xk, which is transmitted signal, and an additive noise added to every received signal sample, nk. xk in this example, we'll assume it is either it can be plus a or it can be minus a, and let's assume it's equiprobable. The probability that it can be plus a or minus a is going to be exactly equal to half. And to that we are adding a Gaussian random variable which is independent of the statistics of x. X and nk are completely independent of each other. In that case, rk now will become a random variable because nk is a random variable and xk is also a random variable. So whenever xk is plus a, then you will get a Gaussian random variable with mean a, and the variance will be same as the noise variance sigma n square. And similarly, if you are transmitting minus a, the mean of the Gaussian rk will be a Gaussian random variable with mean minus a and a variance given by sigma n square. And this is a standard problem. We have already solved this. How do you find the probability of error? Given that I am transmitting plus a, what is the probability that I am going to receive minus a? That is simply nothing but the area under this graph, which is the tail probability. So I should just take this function and integrate it. And that we discussed in the previous lectures. That area is simply, if you know where d is the distance between the two constellation points, then we said q of d by 2 sigma n is the equation that you have to use. So your bit error rate is given by this. Now d here is 2a, plus a and minus a, the distance is 2a, divided by 2 sigma n, so you will be left with q of a by sigma n. For a passband communication system, I can write the signal power divided by the noise power as a square by 2 divided by sigma n square by 2. Okay, a square by 2 divided by sigma n square by 2 will be can be expressed as your signal power divided by noise power. That will be your SNR, and that is a square by sigma n square. For a for a baseband signal, it will be a square itself. Okay, I think one of you had asked why it was q of 2 EB by n naught. That factor comes here. It's not a big deal. It's just a small factor. Okay, so it will simply be 2 square root of SNR itself for a passband communication. So q of root of SNR, I am just writing a by sigma as there is here. It is a square by sigma n square is SNR. And so therefore root of SNR is a by sigma n. I'm sure, if there is a mistake, you can point it out, but it's okay. The more important point is to understand that it is q of root of SNR. So that's the most important point to understand here. So we will just look at this result and try to see what does it intuitively mean. So first I'll assume SNR is 0 dB, which means, SNR is 0, value 0, ratio of powers is 0, which means you can have a 0 dB SNR either if your noise power is infinity or if your signal power is 0. If your signal power is 0, you will get SNR as 0, ratio of 2 powers. It's signal power divided by noise power, PS by PN. If your PS is 0, you will get SNR as 0, or finite PS but PN is infinity. Either cases you will get SNR as 0. If your SNR is 0, then what will happen, I can just write this received vector rk, I am showing it here. Your rk is simply going to be equal to nk itself. I'll assume xk is 0, because if xk is 0, signal power is 0 purely whatever receiving is entirely noise. If what you are receiving is entirely noise, if you look at this graph, the graph that I have shown here, this graph here, both these graphs will collapse. They both will actually overlap at origin. So now, if you want to find the probability that the signal lies on either sides is simply equal to half, right? It's just half of an integral of a Gaussian function. So it will be simply be equal to half. I'll discuss it a little bit more when I go to the next problem, but if you got it, it's good. Or we can simply see, if SNR is 0, you get Q of 0, which is equal to half, right? Q of 0 is nothing but, it's by definition, Q of x is x to infinity, integral of the Gaussian function from x to infinity. So if I integrate it from origin, this is half of the area, which will be half of the area of a PDF function, probability density function, so you will get half. So that will simply be equal to half. So what you get, the limiting value when you have a 0 SNR or minus infinity dB. I mean, SNR of 0 also means minus, that is, if you take 10 log of 0, you will get minus infinity. For that, the bit error rate is half. And this makes intuitive sense, because it's, I mean, we have assumed your input symbols are both equally likely. So which means you don't need, there is no communication happening at all. You don't need a communication at all. At the receiver, you might as well generate the symbols on your own and then give it to a random receiver. I mean, a threshold receiver, which will use this, less than or greater than 0 to detect which symbol was transmitted. I am still, that system is as good as this system with 0 SNR. So there is no communication at all. So that's why you have a maximum entropy condition, which is half, So both are equally likely. The bit error rate is just half. So every bit, the probability that every bit will be in error is exact 50%. Okay. Now let's assume the noise is purely random. It's purely random. It's completely random. It's not selective at all. It's purely random. And you find out that it's a binary system and the detection probability of error is 90%. That cannot happen, because then you know that obviously there is a mistake with your receiver structure, and you will simply flip your receiver structure and you can get 10% probability of error. So here I am assuming noise is non-discriminating. It's completely random. Okay. In that case, and you find out that the probability of error is 90, then it means that, okay, there is something wrong. You will just flip your threshold condition. So the worst case probability of error is simply half, 50%. If it is 50%, you can't do anything. Okay. That's the worst probability of error you can get. And it makes perfect intuitive sense. It's like there is no communication happening at all. You might as well perform the experiment at the receiver yourself without even having a transmitter. Okay, and still get a probability of error of half. Now the next condition is the limiting condition when SNR is infinity. SNR infinity happens when sigma n is 0. When your noise variance is 0, then I can get SNR as infinity, or signal power can also be infinity. First, I'll take the case of sigma n is 0. If sigma n is 0, the constellation points will simply exactly sit put at plus or minus a. There is no variation on the constellation values. So because of that, obviously, if a was plus a was transmitted, you are always going to get plus a. I mean, your threshold detector is going to detect it perfectly. So there will be 0 probability of error. So if your SNR is infinity, it's going to go to 0. So that makes intuitive sense. And this is Q of root SNR. Q of root SNR. So therefore, as you plot it as a function of SNR, Q function, if you see, it's an exponentially decaying function. Okay, it's a tail probability function. As you increase x, the value of Q will decay significantly. So therefore, the curve will look like this, like a waterfall curve. So suddenly, it will be initially a little bit slow, but as SNR increases, it will be a very sharp fall. And it will go to 0. Okay, bit error rate will go to 0 for large values of SNR. So one typical example, this is a useful value, like for example, if you want a bit error rate in 1 in a million bit error, you need an SNR of 13.6 decibels. So from that you can compute the ratio of signal power to noise power. Okay. So this is a standard binary channel, a standard binary symbol transmission, plus minus a, and we saw how the bit error rate is dependent on the signal to noise ratio. This is something we are well aware of. This is what we did in the previous assignment. In this assignment, what I did is that because we are speaking about wireless channels, we introduced a model called as an attenuating channel. Your received signal is no longer just a constant xk or some constant multiplied value, it is getting multiplied by a random variable c. So the received signal is actually c into x of k. Instead of just x of k, it is actually c into x of k plus n of k. Noise is added after that. Okay, so your channel is completely random. So that's what this model means. And this is a typical scenario in a wireless communication system. So we also discussed why the channel is random in some previous examples. You can have moving vehicles and all that. So all that will lead to some sudden changes in your signal power. So we said the received signal itself can be quite random. In the question it's given we have given the statistics of C. It's a normal Gaussian distribution with mean of half and variance of 0.25, or sigma c is half and mu c is half. This is what is given to you in the question. You are now supposed to find what will be the probability of error, bit error rate in a scenario like this. So this is a very, very interesting problem. That's why I thought, in fact I gave two flavors of attenuating channels. So that's why I wanted to explain everything that we can in these two questions. So let's start with this simple problem, which is Rk is C into Xk plus Nk. So first I'll tell you the theory, then we'll come to how to simulate this channel, how to simulate this in an assignment. I'll discuss that as well. So Rk is C into Xk plus Nk. So that's your received signal. So first we'll go for 0 SNR condition. So 0 SNR means there is no received signal. So I'll assume that is 0. So your Rk will exactly be equal to Nk. So because it is Nk, then if you look at your received signal will simply be purely noise. So if I just use a greater than 0 and less than 0 threshold detector, the probability of error is simply going to be half. Right? It's pure noise. I mean, there is a 50% probability that your signal will lie here and signal will lie here. Okay, so that's how you get a probability of error as half. Okay, we'll derive the exact expression later, but I'm just giving you a hint. Even before, your received signal is simply Nk, and you have to, if your received signal is Nk and you are going to use a threshold detector, if your signal is greater than 0, then you will say bit 1 is transmitted. So what is the probability bit 1 is transmitted? Will simply be the area under this curve, this part of the curve. And that will simply be half. So the probability that bit 1 is transmitted but bit minus 1 is received will simply be also equal to half. So this is, I said, the worst case probability, error probability system. There is no transmission at all. I mean, it's as good as having no communication at all. So this is clear for us. When you have 0 SNR, I am going to get a bit error rate of half. The next is we will go for the extreme case. The extreme case is SNR of infinity. In that case, I'll assume sigma n is 0. But what about your received signal? Your received signal is C into X of k. So that received signal in received signal, it's actually C into X of k. So previously, if X of k was plus A, there was no way in an AWGN channel, once you made noise 0, there was no way this signal could be misinterpreted as minus A. But now, because you have multiplied it by a factor C, and C happens to be a Gaussian random variable, if this received transmitted symbol is plus A, you are going to get Rk as AC, A into C. If it is minus A, you will get minus A into C. So if it is plus A, C is a Gaussian random variable, you multiply it with a factor, it's going to be a Gaussian random variable as well. If let's assume mu is the mean of the Gaussian random variable, and sigma square is the variance of the sigma square, and mu c is the mean of the random variable c, Gaussian random variable c, and sigma c square is the variance of the Gaussian random variable c, then if I multiply it by A, what will happen is that your mean will get multiplied by A and your variance will get multiplied by A square. So keeping this in mind, we discussed in this question, mu c is half and sigma c square is 1 by 4. So from that I can say you will actually have two Gaussian distributed. Received signal will be a purely random signal now with mean at A by 2, and this for the other guy it's minus A by 2, and variance is A square by 4. Now if you see, even if I am having no noise in the system, even if there is no noise in the system, there is a finite probability of error, because this function is actually lying on the left of plane, I mean the negative axis. Okay, so there will be a finite area. The area under this is the probability of error, so you will get a probability of error. And what is the probability of error? This looks like a Gaussian function, so we already know that standard equation Q of d by 2 sigma. So we'll just have to use it. So d in this case is a divided by 2 into sigma c, a by 2 sigma c, this is a divided by 2 sigma, where sigma here is the variance of this Gaussian function, and that is simply 2 into sigma c, which is a square by 4, root of a square by 4, that is a by 2. So you will get a and a will cancel out, you will get q of 1. So this is a very, very interesting result. So previously if you saw that when there was no noise, the probability of error was exactly equal to 0 because there was no randomness in your received signal. But now because of this attenuating factor c, there is some kind of randomness. You might actually, even though you transmitted plus a, even if there is no noise, there is a finite probability that the received signal can be negative. Okay, and that turns out to be equal to q of 1. So what we see here is that initially you started at q of 0, which is half, but eventually the steady state, when you make SNR as infinity here, the probability of error is going to be equal to q of 1, and q of 1 is a small number. You can find the value of q of 1 from tables. So how does the function in between going to look like? This we can very easily solve for this problem. I'll just quickly use the problem of very simple understanding of Gaussian random variables. So if you see Rk equals C xk plus Nk. Nk is a Gaussian random variable. C into x of k is also a Gaussian random variable, because if I assume xk is plus a, you are going to get AC plus Nk. Now AC is again a Gaussian random variable. We saw what its mean and variance are. Nk is a zero mean Gaussian random variable, and C, the variance is 1 by 4 and mean is half. So for this, now I have to state this very important thing. C and Nk are assumed to be independent of each other, because that's the assumption we are making, because they both are independent. Channel and noise that you are going to add, it's a very good assumption. They both are independent. Because they are independent, when you add two Gaussian random variables, independent Gaussian random variables, the sum will also be, the resulting sum will also be a Gaussian random variable with a mean equal to the sum of the two means and variance equal to the sum of the two variances. This is a pretty standard theorem. This holds true if they are independent of each other. If they are dependent, if there is some kind of a correlation between the two random variables, then the expressions will slightly change. The variance will definitely change, mean may not change, but variance will change. So that is, we won't be covering that part. We'll only cover independent random variables. So because xk and nk are independent, the resulting random variable will also be a Gaussian random variable with a mean given by the sum of the two means. The first variable's mean is a by 2, second variable's mean is 0, so that will be a by 2 itself. The first variable is a into sigma c square. Sigma c square is 1 by 4, so a square by 2, a square by 4. So this will be a square by 4 plus sigma n square. So this will be your new Gaussian random variable. So that's what I've shown here. In an AWGN channel, there was no term a square by 4 did not exist. But now, because of an attenuating randomness, you are going to get this term here. Okay, the randomness is introduced because of the random attenuation factor. Now again we have the same problem. We have two Gaussian functions separated by a distance d, but the variance is now given by sigma n square plus a square by 4. So we know the standard formula, we will just use it, which will be q of d by 2 sigma, and d in this case is a by 2 plus a by 2, which is a, divided by 2 into sigma, which will be sigma n square plus a square by 4, and finally you will get this result. Q of root of a square by a square plus 4 sigma n square. Okay, if you see, we can actually slightly modify this result. You can actually write it as q of root of SNR by SNR plus 4. You can write it as this way as well. So from this equation itself, you can see that if SNR becomes equal to infinity, okay, if SNR becomes equal to infinity, okay, you will be left with 1. Okay, I'm not sure if there is a small calculation mistake somewhere. You're supposed to get Q of 1. I think if SNR tends to, yeah, you get 1. I'm sorry, this is fine. So you'll get SNR of 1, and if SNR is 0, you will get Q of 0. This expression is fine, I'm sorry. Okay, so this expression is fine. I've just taken sigma n square common out from this, so you will get SNR by SNR plus 4. So you can see if SNR is 0, it will be Q of 0, which is half. If SNR is infinity, you will get Q of 1. So this is the general expression. Now how do you simulate this? I just made a small mistake while giving out the question, because when I simulated it differently, but typing the question, the hint I gave was not accurate here. So I said you have to find the average BER, not just BER. I think it is true, you have to find the average BER, and you have to find the BER for different values of C and then take its average. So this can come across as little, this will be fine for mathematical analysis, but this can come across as little bit confusing for simulations. So how do you simulate this? How do you simulate this assignment? You know how to simulate an additive white Gaussian noise. So first generate random samples xk. So you can generate your random samples xk plus or minus a. Okay. Then multiply it with the random variable c. Now that has to be generated. The variance and mean of this is given to you. So let's say you run the experiment for 1e7 symbols. So 1e power 7 symbols, you are going to run this experiment. Then you have to generate this xk for 1e7 samples. For each of those 1e7 samples, you have to generate the coefficient c. Okay, you can again generate c from a Gaussian random variable. The length of the Gaussian random variable will be same as xk. So then you have to multiply point-wise. You have to multiply c and xk. Then to this you just add nk. Nk is again a Gaussian random variable whose sigma n square can be found. N0 is known. You know how to compute it from N0. Okay, so N0 by 2 and all that, you can use that. Okay, use that, and from that compute your nk. You can generate the random variable nk. Now add the two, then apply your threshold detection, less than or greater than 0. That's it, and you will very clearly get this graph. You can in fact plot this graph as well. You will get this graph. Mathematical equation, you can plot it and you can verify it. You will actually get this graph. Where is it? Yeah, here. This is the graph you will get. But this is, you should understand, this is more of an impractical system. Generally, we will, I'll discuss it in the fourth problem as well. You won't get this saturation will not happen. It will happen under these conditions. Okay, you can see that, you can ask me why is that, intuitively why is it saturating? If I'm going to increase my signal to noise ratio, I'm increasing the spacing. Okay, I'm actually increasing the spacing between the two symbols. But what you are doing is that in this specific example, if you see, the variance of this noise process is also increasing in proportion to the signal power. That's the problem. Okay, that is why as you increase that, even though you are increasing the spacing, the variance is also increasing. So that is why eventually the probability of error will saturate. It will become a constant. So when the variance or the spread of this increases, then you are prone to making more errors. Okay, if the distance increases between the two samples, the distance increases, then you are prone to making less errors. But that is compensated, whatever advantage you are gaining by increasing the distance, it is compensated by an increase in the variance. So that is why you don't get any benefit and this beta rate flattens out. Okay, so that's it about this problem. Then finally we'll discuss the third and the important one is it's a similar problem. The only difference is that the random variable c here now happens to be a Rayleigh random variable. And I already discussed how to generate a Rayleigh random variable in the previous lecture. Okay, so follow that. You just take two Gaussian random variables. I've given the mean of the Rayleigh random variable. I think mean is root of pi by 2 into sigma. So from that you can calculate the sigma of the variable sigma. Then once you know sigma, you know the variance of the two random variables x square plus y square. You know the sigmas of both. They both are zero mean, but you know sigma, so you can generate the random variable. Now once you know c, you can just do the experiment in the same way as it is. Now the only difference is c is a Rayleigh random variable compared to question number 2. So which means c will take on values from 0 to infinity only. If you see previously in the question number 2, c could take values from minus infinity to plus infinity because it was a purely Gaussian function. But now C can take only values from 0 to infinity. So we will see how does this change. We will do a similar intuitive analysis, mathematical analysis, and then I'll tell you quickly how to simulate it as well. So here, this is the problem. We have an attenuating channel, which is a random attenuating channel, and an additive white Gaussian noise. That's your received signal vector. So first is a standard case. We'll assume for SNR equal to 0. If SNR is 0, your signal power itself is 0. So you will receive only noise. So obviously the bit error rate is going to be half. 50% probability that you will make an error in detection. But that's very, very trivial. Now what happens when you have SNR of infinity? That's a problem we'll analyze. If SNR is infinity, that can happen if your noise power is 0, right? If your noise power is 0 or signal power can be infinity. Either cases SNR can be infinity. So I'll take an easier case, which is noise is 0. Then your received vector is simply going to be equal to x in xk into c. And what is c? C, we know, is a Rayleigh random variable given by this. So Rayleigh random variable will look like this. It will start at 0 and then it will go like this. The peak value occurs, I think, at sigma, that's what sigma c here. So this is something we are already aware of. Now when I multiply it with a, what is going to happen is that the variance is going to get, the sigma is going to get multiplied by a, mean, everything is going to get multiplied by the factor a. Variance will get multiplied by a square, but standard deviation sigma, the new sigma c will be multiplied by a. So now I'll plot these two random variables on the constellation axis or on the signal diagram. Okay. So when you draw this here, if you notice, since at 0 signal power, this is also the probability is 0. So this is one Rayleigh random variable, and I've multiplied it by a here because it gets scaled. Everything, the product gets, the x-axis is getting multiplied by a. So you get that. Okay. So this will be the shape of this function. Now if you observe this function, there is really no overlap. There is no overlap happening at origin. If let's say this symbol was transmitted, plus a was transmitted, there is no way this will be negative, because your c, the multiplicative factor, is always 0 to infinity. It's never negative. So the received symbol will, if you transmitted plus a, you will never receive a minus a in the absence of noise. So therefore, if I use this as a threshold detection point, then I can clearly say the probability of error is 0. So this is clear. So if I make an infinite SNR, the probability of error is 0. If I assume a 0 SNR, the probability of error is half. So this looks like fine. This is what we expected even in a simple additive white Gaussian noise channel. The graph was like this. It started at 0 and then finally it started at half. At SNR of 0 you get half, and finally it goes to 0 at SNR of infinity. Okay. Now the question is, because there is an additive factor c here, there is a multiplicative factor c here, what difference does it make? The end values are same. The end values are same. But what about the values in between? How gracefully or how fast this function goes to infinity at 0? Okay. How fast does it go to 0 compared to an AWGN channel? So that's what we'll be trying to show here. So to solve the problem, I'll just directly come to this, which is Rk is C into xk plus nk. Okay. So first we'll assume that C is a constant. First, for the time being, we'll assume C is a constant. If C is a constant, then it's going to be Cxk plus nk. So the received symbol is going to be AC or minus AC, and there will be some additive white Gaussian noise added to it. And the variance of this Gaussian noise is going to be sigma n square. And we know the probability of error for that is going to be Q of d by 2 sigma n. So here d is 2AC by 2 into sigma n, so you will get AC by sigma n. Now mind you, I asked you to find the average bit error rate. Here C is a random variable. Okay. So if I ask you to find the average random variable, average bit error rate, that will be simply expected value or the mean value of Q of AC by sigma n. The mean, the average value of that. And this we already said how to compute in the previous lectures. So if I have a function g of x where x is a random variable, so the average value, the mean value of the function is simply given by this. So you will take the value multiplied by the probability density function and integrate it from 0 to infinity. Now we know Q of x, the function Q of x can also be expressed as integral x to infinity e power minus x square by 2 dx. So expand this again. This is again a very standard problem. How to integrate this? This is you get a double integral here. Okay. So you will get a double integral here, and solving a double integral is not really difficult. So you can very easily solve. I mean, if you know a little bit of math, it's okay. But again, I really don't expect you to remember the procedure and all that. You will find a lot of material on the internet how to solve these integrals. Okay. I'll give you the final result. You should just solve this, changing the order of integration and making a substitution AC by sigma n as x and all that. You will get a slightly simplified integral, and you should just change the order of integration. I'll give the final result. What you get is P average will be half into 1 minus root of SNR by 2 plus SNR. There is no Q function now. It's only given by this. So this result should make sense, because assume SNR is 0, this term will go to 0, so you will be left with half. If you assume SNR as infinity, if I assume SNR as infinity, this term will go to 1 and you will get probability of error as 0. Okay, so this term makes sense. I mean, this equation is fine. But now what happens when I assume large SNRs? So if I assume large SNRs, this expression I can reduce it to something like this: 1 by 1 plus 2 by SNR. And you can use this, you can approximate this to 1 minus half into 1 by SNR into 2. So it will be 1 minus 1 by SNR. Okay, and substitute it here, you will get average bit error rate as 1 by 2 into SNR. So this is a very, very interesting result. Okay, so this is, I'm showing this on a logarithmic scale. On a logarithmic scale, 1 by SNR, if you take 10 log of it, you will get a linear line with a negative slope. So that's why I've shown it here. This is a logarithmic axis. So bit error rate EB by N naught, SNR is on logarithmic in decibels. See, understand this 1 by 2 SNR is not in decibels. This is in, ratio of powers. But if I take 10 log of that, I'll get a linear line like this. But if you recall, for a pure additive white Gaussian noise channel, it would just go down exponentially, because it was Q of x, Q of EB by N naught or D by 2 sigma. Okay, or I can write Q of root of SNR. Okay, this was an exponentially decaying function. It will just reduce significantly even if you increase the SNR by slight amounts. But if you look at this, this is much more graceful decrease. Okay, the decrease, even if you increase your SNR by significant amounts, the returns you will get in bit error rate will not be so high. That's the major problem of a wireless communication system. A wireless communication system, when you compare it with a wired communication, so why this is a wired communication system or a line of sight communication system, okay, where in a line of sight system also can be approximated to a wired system, where the received power is more or less constant. There isn't big attenuations there. Okay, and there is no multipaths and all that. So when I say line of sight, there is only one direct sight between transmitter and receiver. There are no multiple paths. In that case, if you see this, the bit error rate reduces significantly when you increase SNR. So for the same SNR, you will get a much higher probability of error in a wireless communication system. So that is why if I want to get same bit error rate, I have to burn much more power. I mean, I have to have a much higher SNR. See, this is the same bit error rate. Let's say I choose 10 power minus 6. This point was turning out to be 13 point some dB, 13.6 or something, I forgot the number, some 13 dB or so. But this will be much higher. I mean, it will be like 20 decibels or so. I mean, I'm just giving a number off the head, but this can be really, really large. So your SNR necessary, for you to get same bit error rate of 10 power minus 6, you have to spend much larger power in a wireless communication system. Okay, that's the main disadvantage of a wireless communication system. That's called fading. Okay, your received signal power will be multiplied by a random number C, and that causes all the difference. That creates a lot of problems for us. You have to burn more power to get the comparable performance of a wired communications. But still, why is wireless so popular? Why is wireless communication so popular? It's because sometimes when you have the distance keeps increasing between the transmitter and receiver, sometimes you can't even build a proper communication channel. I mean, a wired communication may not even be possible to build. So in that case, wireless becomes much easier. Okay, but now we do a lot more things to get low bit error rates. But this is just comparing a simple wireless versus wired channel with the simple relay model. The next question is, why did we assume Rayleigh model for a wireless channel? That I'll answer in the next few lectures. In fact, where do we get a Rayleigh model at all? How do I just randomly assumed it a Rayleigh fading. What exactly is a Rayleigh fading? Why do we get it? In the next few lectures, I'll very briefly explain that. Okay, so that will be your syllabus for extra syllabus for Compre. If I feel that you don't have time for preparing, I'll reduce that portions in the syllabus. I'll explain the lectures, but I'll ensure you don't get any questions or very few questions from those topics. Okay, so that's it. I think you will be able to solve this assignment now. So in fact, it's pretty trivial to solve. So I've already given you all the hints to solve it. So all you need to do in this channel again is generate random variable xk, which is plus or minus a. Again, you know how to generate this. Generate 1E7 samples, and then generate a random variable c. This should be a Rayleigh random variable, and I told you how to generate it using 2 Gaussian random variables. So that's the first part of the question, and you're supposed to plot C as well. That's also there in the second part. Third part, I think. Third question also has that, I think, how to plot it. So once you know how to do it, you can apply the similar thing here. So you have to generate the random variable C. You have to write a function how to generate random variable using 2 Gaussian random variables. Just use this x square plus y square root of this. Okay, and x and y are Gaussian random variables. The means of it can be computed from the data given. Okay, mean and variance of it. Okay, mean is 0 anyways. Variance you can compute it from the data given. So then you have C, and you should have 1E7 samples of C, 1E7 samples of xk, and then you should have 1E7 samples of nk. Then just perform this equation, which is C into xk plus nk. This will be your received vector. And then to each of the samples, see, in MATLAB it's always better to write codes as a vector. You don't run for loops, minimize for loops as much as you can. And then compare all the vectors, elements in this vector with this is a 1E7 vector, 1 cross 1E7 vector. Compare each of the elements to 0. If it is greater than 0, then bit A is transmitted, less than 0, bit minus A is transmitted, or bit 1 or bit 0 is transmitted. Okay, so finally, then you know how to compute probability of error. So you have the received bits, and then you have the transmitted bits, compare the two, take the difference, and find how many errors are there. Number of errors divided by the total bit length will give you the total symbol length, which is 1E7, will give you the bit error rate. Okay, you can directly plot it. It's a pretty quick simulation. It will run very fast. But I wanted you to understand why are we doing these problems. Okay, so we are trying to capture the effect of a wireless channel model, and then we are trying to show it to a wired communication system. I gave one more tweak, which is question number 2. That is not a realistic case. I just took an example just to tell you, okay, look, Gaussian is different, Rayleigh is different. Okay, we were getting some weird flattened curve for the question number 2. Okay, you won't get that in a practical scenario. Okay, I can't exactly say that, but generally we won't get it. And it makes intuitive sense because your C is an attenuation factor. It can be 0 to infinity. Okay, unless you accidentally flip the symbol or there is a phase change, it can happen. Phase change can happen, but it's very, very rare. Okay, so this is enough, and why don't you solve it? In case you have any doubts, just send me an email. I'll reply back.